afternoon. My name is Hella and I'm part of Mr. Martinez's free calculus group to explain why conics are so important. Like honestly, why are we even regarding them? Why are they a part of our unit? Well, one of the major things that you have to understand is that conics are a huge part of nature, as it says in this handy dandy PDF file. It states that conic sections are important because they model important physical processes in nature. It can be shown that any body under the influence of an inverse square law force must have a trajectory of one of the conic sections. And these again are the hyperbola, the parabola, the ellipse, and the circle. Heavenly bodies attract each other with a gravitational force that is inversely proportional to the square of the distance between them. This law, Newton's law of gravitation, which is seen in physics, is an example of the inverse square law. Hence, the trajectories of the heavenly bodies are conic sections. Again, parabolas, hyperbolas, circles, and ellipses. And also, Coulomb's law of attraction of charged particles is another example of the inverse square law. Therefore, the trajectories of charged particles, for example the electrons, because those are the ones that are charged, are conic sections. So, from the large scale of the universe to the microscopic scale of the atom, conic sections occur in nature. So again, you have it in physics, where you have Newton's law of gravitation. You have an example from Coulomb's law, which also is the inverse square law. And you have other examples, such as the Mandelbrot set, which occurs in every type of nature, either be it from a tree, be it from a flower, be it from our own earth, where it comes like that. So that's why conic sections are so important, because they happen in nature. Thank you so much for listening.
Basic equation for a flower is R equals A sine B theta and R equals A cosine B theta. So the basic rule is A determines the length of the petal and B determines the number of petals. Now, if B is even, you double the value of B to get the number of petals. And if it's odd, the value of B stays the same. First, we're going to do R equals cosine theta. If cosine is positive, then you start at 0 degrees. If cosine is negative, you start at 180 degrees. Since we're graphing cosine theta, it's positive, and we're going to start at 0 degrees. So the values of A and B in this equation are 1. So we're going to have only one petal, and it's going to be 1 long. So we're going to pretend that this is all 1. So this is 1, 0. Cosine, you always graph it at, you pretend this is the x-axis. You graph it at this pole. So basically it's going to look like that. We are going to do R equals sine theta. If it's positive, then you take a 90 degrees and you divide it by the value of B. If it's negative, you just draw it on the opposite quadrant that you get from this. Since this is positive sine theta, we know that it's going to start right here. This is 0, 1. The value of all of these are 1. And since B is 1 and A is also 1, the length will be 1 and there will be only one petal, and that's how sine theta looks.
Okay, so our first example is going to be a cosine example, and it's pretty straightforward for the most part. So the equation is R equals -4 cosine 2 theta. Right off the bat, we can tell that our petal length is going to be 4 due to this coefficient right here, the coefficient of the cosine. And We're going to have 4 petals because the coefficient of the theta, the 2 right here, is an even number, and you need to double that if it's even. So 4 petals. Since this is actually a negative cosine, the first petal is going to be at 180 degrees. And last but not least, for the spacing, to find the spacing you need to do 360, which represents like all of the polar graph, divided by the number of petals, which in this case is 4. So the spacing would be 90 degrees. Drawing this, we know that our first petal is going to be at 180 degrees, which would be right here. And it has to be, yeah, we're starting here. So it would go like a little bit like this. Yes, like that. I mean, obviously these petals are supposed to be equal in size and everything, and each of them are 4 in length. They're not supposed to overlap either. My picture isn't perfect, but that's what it's supposed to be. So this is 4, 4, 4, and they should have 90 degrees in between. All of them. So for another example, we're going to do an equation that doesn't really turn out to look like a flower, but it does follow the equation of a flower. So, oh, we forgot our graph. So our equation in this case is going to be r equals negative 3 cosine theta. We can tell that because of this coefficient, it's going to have a petal length of 3. Okay, so the number of petals, like we mentioned before, depends on the coefficient of the theta and whether it's odd or even. And in this case, it's just 1, and that's an odd number, so you'd only have 1 petal. Essentially, that would turn into a circle, but it does follow the equation of a flower, so we'll just go ahead and, wait, that's not supposed to be there. So graphing that, it is going to be a negative cosine, so it would be it would start at 180. Graphing that would just look like this. That's 3, because of the petal length. And then the point here, and you just draw a circle. It has to hit the pole, and also it goes around twice because it's a circle, but like I said, doesn't look like a flower, it's just 1 petal, but it does follow the equation.
Okay, our third example is going to be a sine graph. So what you have to mark first is your A and B, and your A is 8, and your B is actually 1. So you know, since B is 1, there's only going to be 1 petal. Okay, so if you have your axes, you know that the sign is negative, so it's going to be on the lower quadrant. And so your sine graph practically looks like this. So what's important to note that your length, which is A, is 8. So this length right here is 8. So that's practically what your sine graph would look like. Our next example is r equals 2 sine 3 theta. So what's important is to mark your A and your B next. So once you have your graph, you know your signs are generally going to be like in these areas, and they can touch the polar axis. But, well, what's to note first is that how many petals you are going to have. So you're going to have 3 petals because B is odd, so it's just the same number. And then your length is 2, but so practically what your sine graph is going to look like is something along the lines of this. You have 3 petals, and the length is 2. What's good to know when you're graphing your signs
is the distance between each petal. So you can find that out by getting 360 divided by B. So since you have 3 petals, it's 360 divided by 3, so each petal is 120 degrees apart. So the distance between here and here is 120 degrees. So that's how you graph.